Hello friends, in this video let us discuss about the working principle of stepper motor. So there are many industrial applications, or you can say industrial situations, which call for precise positioning of object or precise control of speed without resorting to any feedback system. So your stepper motor is suited for such tasks where you can have precise positioning of object as well as precise control of speed without resorting to any feedback. So your stepper motor rotates a precise angular your stepper motor rotates at a precise angular distance, which is nothing but one step for each pulse provided to the drive circuit. So there will be a drive circuit and your stepper motor rotates at a precise angular distance, which is nothing but a step for each pulse applied or provided to the drive circuit. So let us take a stepper motor which is having the step angle 7.5 degree per pulse. So if I provide one pulse to this drive circuit, your stepper motor shaft will rotate 7.5 degree per each pulse. So the step angle, it is nothing but the angular movement or the angular rotation of the shaft provided by each pulse expressed in degrees. So your step angle, it is nothing but the angular rotation of the shaft for each pulse provided is nothing but the step angle. So let us consider a stepper motor which is having the step angle of 7 degree per pulse, and in order to place an object you have to rotate the shaft of that stepper motor for 225 degrees. So you have to rotate 225 degrees in order to place an object at a desired position. So let me say earlier you were having an object here, and this object has to be placed at this point. So now it has to rotate 225 degrees to place the earlier object from this position to this position. Now as your stepper motor can having the step angle of 7 degree per pulse, that means in order to rotate 225 degrees, what I do is 225 degrees per 7.5 degree will give you the number of pulses required for the drive circuit. That means for one pulse it will rotate 7.5, for other pulse it will rotate again 7.5, for other pulse 7.5, 7.5, and this can be obtained by dividing this 225 by 7.5, it will give you 30. So 30 pulses should be given to the drive circuit so that the position of the object can be placed at the required place. So you can place at the required position your object in this fashion. So this is how you can precisely place your object at the required place, and this offers the precise control of speed of the motor. So precise open loop speed control, because this stepper motor doesn't employ any feedback like your stepper motor. So it will provide you the precise open loop speed control, because the speed of the shaft depends only on the step pulse frequency. So how many pulses you are applying, the speed of the shaft depends on only this step pulse frequency, and it is independent of load. So whatever the load you are applying to the stepper motor, the speed has nothing to do with it, because your speed depends only on the number of step pulse you are applying to the drive circuit. So if we now talk about what are the stepper motors, so stepper motor, or you can call it as step motor or stepping motor, whatever you call, your stepper motor is a brushless It's a brushless, there are no brushes here. It's a brushless synchronous motor. It's a brushless synchronous motor, but when you consider a synchronous motor, you will be having the brushes and the slip rings so that you can feed your DC supply to the field system present in that synchronous motor. But here the stepper motor is a brushless synchronous motor which divides the full rotation into the number of steps. So it divides the full rotation into number of steps. So this is unlike your brushless DC motor. So in a brushless DC motor, on providing a DC voltage, your shaft rotates in a continuous manner. So there will be a continuous angular rotation of the shaft, but here this stepper motor will rotate in the discrete steps. So discrete angular steps. So this is the main difference you find between the brushless DC motor and the brushless synchronous motor. This brushless synchronous motor will rotate at a discrete, it will rotate in discrete steps, whereas your brushless DC motor will have a continuous angular rotation of the shaft. So basically your stepper motor can have the steps per revolution, like it can have 12 steps per revolution. That means it can 12 steps per revolution. 12 steps per revolution. One revolution is 360 degrees. So 12 steps per revolution. That means it can complete the 360 degree revolution in 12 steps. That means you can say each steps covers a degree of 12 into x will give you 360 degrees. So each x is nothing but the degree per step, that is nothing but the resolution of the stepper motor. So 12 into 30 will give you 360 degrees. That means each degree must, each step must rotate at a degree of 30 degrees. So each step should comprise of 30 degrees per step. So your stepper motors can have the steps per revolution like 12, 24, 72, 144, 180 and 200. So this is nothing but 12 into x is equal to 360. Just here x is nothing but the degrees per step, that is nothing but the resolution of the motor, and again here we are having the step angle, that is 30 degrees, and here you will be having this 24 into 15 degrees, and this will be 5 degrees, and here this will be 2.5 degrees per step. So it will have to rotate 2.5 degrees per pulse or per step. So pulse is nothing but a step here. So 2.5 degree per pulse or per step, and this is 2 degree, and this will be 1.8 degree. So your stepper motor will have the smallest step angle like 0.72 degrees, and it can have the largest step angle like 90 degrees. It can have both the step angles 0.72 and 90 degrees, and your stepper motor is an extraordinary operating motor. The highest stepping angle, that is, it can have the highest stepping rate 20,000 steps per second. 20,000 steps it can move in a single second. So that is the extraordinary operating capability of the brushless synchronous motor, which is nothing but your stepper motor, and at this high stepping rate the shaft will appear to move continuously, but you have to know that it is operating in steps. So but as you witness the shaft rotation, it will appear like a continuous shaft rotation. So it will move at 20,000 steps per second, and at this 20,000 steps per second, which is with this high pulse rate or high stepping rate, the shaft will appear to move in continuous manner, and this high speed operation of motor can be termed as sleeving. So this is an important term. At high speed operation the motor can be said to be sleeving, and if you suddenly stop giving pulses to the motor instead of decreasing or slowing down progressively, then the motor loses synchronism and stops suddenly. So if you remember this, if you stop giving pulses suddenly instead of reducing the speed gradually, the motor loses synchronism and comes to a halt position immediately. And now if we talk about the advantages of these brushless synchronous motors, so you can say one advantage is the rotor can be held in a fixed position for a long time on supplying a rated current to the stator windings. So it will be, the rotor can be held in a fixed position. It can be held in a fixed position for a long amount of time by applying a rated current to the stator windings. That means there is no problem of stalling here. So no stalling problem. This is one advantage. And if we talk about the two main advantages of this brushless synchronous motor or the stepper motor is, so the out of the two main advantages, one advantage is, it is here, as you can see, the steps, this is the step pulse frequency or the steps can be digitally counted. So the steps can be digitally counted and the motor can be stopped when the desired position is reached. So these stepper motor lends themselves to be controlled by programmable controllers or microprocessors or computers. So they are digitally compatible. This is the main advantage of your stepper motor, and the explosive growth of computers gave a great demand for the stepper motors as they are digitally compatible with the microprocessors, computers and programmable controllers. And the second advantage is, that is the second main advantage is, here we do not require any sensors like in servo motors to sense the position and the speed. So if you want to know the position of the shaft of the stepper motor, then you can simply count the number of input pulses. So by knowing the number of input pulses, you can easily come to know about the position of the shaft. And if you want to know the speed of the stepper motor, then you can go for the periodic counting. So you can go for the periodic counting of the pulses to know the speed of the stepper motor. So these are the two main advantages of this stepper motor. And if you see the applications of this stepper motor, they will find applications in the holding and positioning applications, in the field of laser and optics and image scanners, 3D printers, and you can say in the floppy disk drives, compact disk drives, plotters, and in camera lenses. So a wide variety of applications can be found of this stepper motor. Now if we talk about the step angle in detail, the step angle is nothing but the angle of the shaft. There is an angular rotation of the shaft for each pulse provided to the drive circuit. So smaller the step angle, if I say you are having a very smaller step angle, let me consider you having some step angle of 0.72 degrees, that is a degree per pulse. So if you provide a one pulse, it will rotate it at a degree of, that is a step angle of 0.72 degree. So smaller the step angle, so if I say smaller step angle, that means you need the higher step per resolution, because if you take this 1.8 degree, you are having a higher step per revolution, that is 200 steps per revolution. Now if you take the some greater step angle, it will require a lower step per revolution. So for a smaller step angle, we require higher step per resolution, that is higher step per revolution, and this higher step per revolution is higher resolution. Resolution is the degree per step, and this higher resolution will result in the accuracy of the positioning of objects by the stepper motor. So if I talk about the mathematical expression of finding the step angle, so if you say you are having the stator phases and the number of rotor tails, then the step angle alpha can be given by 360 degree upon n into nr, where nr is the number of rotor teeth, M is the number of stator phases. Now in case if you do not know the number of stator phases and you know the number of rotor poles or rotor teeth and stator poles or stator teeth, then you can have your step angle alpha as ns minus nr upon ns into nr into 360 degrees, where ns is the number of stator teeth and nr is the number of rotor teeth. Here do not get confused as stator synchronous speed or rotor synchronous speed. There is a number of stator poles and the number of rotor poles. Now if I talk about the stepper motor system, basically your stepper motor system consists of three basic elements along with some user interface. So along with some user interface you will be having three basic elements of the stepper motor system. So one is the stepper motor itself, in the stepper motor system, and the second one is indexer. So indexer you can call it as a controller, indexer or controller. Basically your indexer is a microprocessor. It's a microprocessor capable of generating the stepping pulses and directional signals required for the driver. So this microprocessor is capable of generating the stepping pulses and directional signals required for the driver. And next, the third component we are having is you can say driver, or you can call it as the amplifier. Now this driver converts the command signals, there is a commanding signals of the indexer, and converts, that is it takes the command signal and converts this command signal so that the you can say it converts to a higher power. So basically this amplifier amplifies these command signals so that you can get high power to energize the stator windings. So this amplifier converts the command signal to such a power that power is able to energize your stator windings, and this driver will be available depending on the voltage rating, current rating and the construction technology. This is about the stepper motor system. So if we talk about the constructional features of the stepper motor, so generally your stepper motor has again two parts, that is stator and the other one is a rotor. So the construction is very simple. It consists of a slotted stator which is equipped with multi-pole. It is equipped with multi-pole, multi-phase winding, multi-pole and with multi-phase winding, which is just similar to the windings of the conventional machines. And here your rotor structure doesn't have any winding, that means the rotor carries no winding on it. So the rotor carries no winding, and here the poles of the stepper motor will be dependent on the required step angle. So it is dependent on the required step angle, and the motor can be having a two-phase windings or three-phase windings or four-phase windings. So this is the multipole and multi-phase winding, and the rotor structure carries no winding, and the rotor can be of permanent magnet or it can be of variable reluctance. So these are the two categories. Now depending on the construction of the motor, these stepper motors can be classified into three types. So one is you are having the permanent magnet stepper motor, and other one is the variable reluctance stepper motor, and the third one is the hybrid stepper motor. So by understanding these three stepper motors, we shall also discuss the working principle while understanding these three motors. So if I know, let me talk about the PMSM, that is the permanent magnet stepper motor. It is not synchronous motor, it is stepper motor, permanent magnet stepper motor. So here you can see there is one pole here, two pole, three pole, four pole. So four pole, this motor is basically four pole stator, that is the stator is having four pole, and 1, 2, 3, 6. 4 pole stator with 6 pole rotor. So we are considering a permanent magnet stepper motor which is having 4 stator poles and 6 rotor poles. Now from here you can calculate the step angle. So your step angle will be nothing but the difference of these poles. So that is here I will do nr minus ns by nr into ns into 360. So this will be 2 upon 6 power 24 and this is 360. So this gives you 30 degrees. So your step angle will be 30 degrees. So basically this permanent magnet stepper motor employs a permanent magnet rotor. So your rotor is a permanent magnet and your stator is wound like this. So here you can see the control switches. So these are your control switches from where you can obtain the pulses. So this is your control switch A, this is B, this is C and this is D. So from control switch A you have wound on the pole A and the end terminal is, this is the end terminal of the winding on pole A, and from control switch B you have wound on the winding wound on the pole B, and this is to the pole C, and from here to the pole D, and all the end terminals of these windings are taken out to a terminal box where you can apply your voltage, DC voltage, and it will be some 10 to 50 volts. So from here you will give your DC voltage that is around 10 to 50 volts. Now the stator construction is like this, and this is your permanent magnet rotor, and the windings are wrapped around the poles in such a way that on the closure of the control switch, the winding or the magnetic pole behaves as a north pole. So if you close this switch and the windings are wrapped in such a way, on closure of this switch, this magnetic pole will behave as a north pole. So this will behave as a north pole and this will behave as a south pole. Or I will do not say anything about this, but the windings are wrapped in such a way this will act as a north pole. So if I explain you clearly, let me say I am having a winding here, and let me say there is some other winding here, and here you are having the rotor. So you have applied a DC voltage here, and the current starts flowing in this fashion. So now if you apply the thumb rule, so the current is flowing in this way and you are having a magnetic field coming out. So the magnetic field is coming out here and it is entering here. So similarly magnetic field is coming out here and it is entering here. So applying the thumb rule. So if you apply the thumb rule, your magnetic field will be coming out here and is entering here. So wherever the magnetic field is coming out, it is north pole, and where it is entering, it is south pole. So similarly here, the windings are wound in such a way that this magnetic pole will behave as a north pole. So similarly, now when you have the north pole here, this north pole will attract your south pole. So rotor will move to a position so that the nearest south pole of the rotor will be aligned with the north pole of the stator. So now if you have here north pole, and if I say somewhere, let me say this is my rotor, some iron bar, this is north pole and this is south pole. So this will attract it to this. So the MMF developed in the pole A will attract the nearest south pole of the rotor so that they get aligned. So similarly, now what I do is I will open this control switch A. Now I will close the control switch B. Now when you close the control switch B, this pole will behave as a north pole. So this pole will behave as a north pole, and what does this north pole? This north pole tries to attract the nearest south pole of the rotor. So your rotor will move, this south pole will move in this direction so that they get attracted. So this south pole will get aligned with this north pole, and now what you do is you excite your control, that is you close your control switch C. Now on closing the control switch C, this will behave again as a north pole and it will attract the nearest rotor south pole. So in this way your rotor keeps on moving in steps, that is the step angle of 30 degrees. So here it will move 30 degrees and again this pole will move 30 degrees like this. So each pole will move 30 degrees on applying each pulse. Now we are we are having a switching sequence like this. First A, B, C, D, and the rotor is moving in this direction, that is in the clockwise direction. Now if you excite first A, and if you excite or energize your winding on the pole D, then your rotor will move in the anti-clockwise direction. So it will move in the counterclockwise direction. So the rotor movement, whether it is in clockwise or the anti-clockwise, depends on the switching sequence, how you are energizing the windings. And here I have drawn the permanent magnet stepper motor with the salient poles in both the rotor and the stator structures. But you can also have the non-salient pole rotor and stator structures. So basically this is your permanent magnet, which is the rotor, which needs no excitation because the magnet itself is the magnetized one, as we are showing the permanent magnet. So there is no need of excitation to this rotor, and you can see your stator. So in the permanent magnet stepper motor, both the rotor and the stator poles can be of non-salient pole type, or it can be of salient pole type. So generally for smaller step angles, you employ the non-salient pole structures. So this is about your permanent magnet stepper motor. Now let us shift to the variable reluctance stepper motor. So if you see this motor, here I am having one phase, this is my second phase, this is the third phase, and this is the fourth phase. So your variable reluctance stepper motor is having 4 phase. It is a 4 phase and 8 poles on the stator, 4 phase, 8 pole stator with 6 pole rotor, 1, 2, 3, 4, 5, 6, with 6 pole rotor is shown here. And from this 4 phase and the 6 pole, we can calculate the step angle, that is alpha will be equal to 360 degree upon, where m is the number of stator phase will be 4, and the number of rotor teeth or the rotor poles will be 6, and this will give you 24 into 15 degrees. So your alpha will be equal to 15 degrees. That means for each pulse provided, the rotor will rotate 15 degrees. The rotor will rotate 15 degrees. So you have seen the phases and the stator poles and the rotor poles. Now the torque developed here is due to the large differences in the magnetic reluctance between the direct axis and the quadrature axis. Now if I tell you about the direct axis and the quadrature axis, so let me say this is my stator, and there is a field magnet in this. So this is your direct axis. On the direct axis, if I say there is a rotor pole here, so the direct axis has a minimum reluctance path, where reluctance is nothing but the opposition offered by the space, or you can say air. So reluctance is a term used in the magnetic circuit, and the resistance is a term used in the electric circuit. So reluctance, which is given by L by mu into A. So here you can see in the direct axis there will be a minimum reluctance to the flux path, and this is your quadrature axis, and in the quadrature axis here you can see there is a large reluctance path. So due to the differences in the magnetic reluctances of these two axes, there will be a torque developed. So similarly, in the variable reluctance stepper motor, variable reluctance is because, so here you can see there is a less reluctance, and here you can see there is a large reluctance, and again here you can see a less reluctance, and here it is again a large reluctance. So that is why it is a variable reluctance. Now here, on applying a DC excitation, a stationary field will be developed. Now this stationary field will generate a torque, or you can say a reluctance torque, and this reluctance torque will move your rotor where the reluctance of the flux path is minimum. So where the magnetic reluctance will be minimum, there the rotor moves and aligns with the stator phases. Suppose if I say the phases, stator phases 1, 1 dash is excited. So let me say stator phases 1, 1 dash is excited, with a DC voltage. So when the phases 1 dash is excited, this will be the position of the rotor poles. So here it is 4, so it is 1. So where the rotor poles 1 and 4 will align with the stator poles 1 1 dash. So for when you excite 1 1 dash, the rotor poles 1 and 4 will align with the stator poles 1 1 dash. So because here the magnetic reluctance will be minimum. So as we have said, the torque developed will move the rotor in such a position where the reluctance of the magnetic flux will be minimum. So now if I excite, now I have turned off the connection to this winding 1 1 dash and now I will excite the phase 2 2 dash. So I will excite the phases 2 2 dash. So when I excite the phases 2 2 dash, again there will be a reluctance torque, and this reluctance torque will move the rotor to a position where there is a minimum reluctance. So for the minimum reluctance, you can see the poles 2 5. Now we have excited the phases 2 2 dash. Now these rotor pole 2 and 5 will move to the minimum reluctance path. So you can see this is the axis, for your phases 2 2 dash. So the rotor poles 2 5 will align with the stator poles 2 2 dash, such that you can see the reluctance experienced by these rotor poles 2 and 5 will become minimum. So this will rotate in the anti-clockwise direction to the 15 degrees, because the step angle is 15 degrees. So this rotor pole 2 5 will align with the stator poles 2 2 dash, just like here the rotor poles 1 and 4 have aligned with the stator poles 1 1 dash. So that when they get aligned, then there will be the minimum reluctance path. So this is how the variable reluctance stepper motor works. And if you want to change the sequence, so this is rotating here in anti-clockwise direction. Now after turning off the excitation to 1 1 dash, if you excite the winding, this winding 4 4 dash, that is 4 dash 4 or 4 4 dash, then your rotor will move in the clockwise direction. So again here, based on the step switching sequence, you can rotate your rotor in the clockwise direction or anti-clockwise direction. Now there is a other term here, we call it as multi-stack variable reluctance stepper motor. So this multi-stack, or if I tell you the definition of stack, the motor is divided into several magnetic isolated sections known as stack through its axial length. So a multi-stack variable reluctance stepper motor can be considered to be M identical single variable reluctance stepper motor where the rotor will be mounted on the same shaft. So for this motor, for the multi-stack VRSM, if I calculate alpha, so your alpha will be equal to 360 degree by where M is the number of identical single stack variable reluctance stepper motor into the rotor teeth NR. So this is alpha for your variable reluctance stepper motor. Now let us move to the third motor, that is hybrid stepper motor. So in the hybrid stepper motor, this hybrid stepper motor is similar to your permanent magnet stepper motor, but the only difference is here the rotor will be having a toothed structure like your variable reluctance stepper motor rotor. So again here it is a permanent magnet, this is a permanent magnet but with a toothed structure. Here the rotor can be with a tooth or non-tooth. That means we have said that it can be a salient pole or it can be a non-salient pole. So here it is a permanent magnet with a toothed structure, and you can see there is a phase 1 1 dash, phase 1 1 dash and the phase 2 2 dash. So there are two phases here. This is a 2 phase 4 pole stator. So stator is having 4 poles and your rotor is having 1 2 3 4 5 6. So 6-pole rotor. So your rotor will be always of even poles, and again stator will also be of even poles. So 4-pole stator, 6-pole rotor, and if you calculate the stepping angle, alpha will be equal to 360 degree by 2 into 6. So this will give you again 30 degrees. So step angle will be 30 degrees. Now when you excite the phases 1 1 dash, when you excite the phases 1 1 dash, again this will behave as a north pole and this will behave as a south pole, so that this north pole, there is a MMF developed and this MMF will attract nearest rotor south pole. So this is how the rotor gets aligned with the stator poles. Now here if you excite the phases 2 2 dash, now you excite the phases 2 2 dash. Now when you excite the phases 2 2 dash, this will behave the north pole and this will behave as a south pole. So at a time only one phase is excited. So remember this, at a time only one phase is excited or one pole winding is excited. So here 2 2 dash is excited, and now the rotor will move in such a manner where the north pole gets attracted to the south pole and the south pole of the rotor will get aligned with the north pole of the stator. So this will move in the anti-clockwise direction such that this rotor will get aligned with this north pole and this north pole of rotor will get aligned with this south pole, and this is how the rotor starts rotating. And again if you change the switching sequence, then you can change the rotation of your rotor. So here I am not discussing about the advantages and the disadvantages of each and each motor. So you can refer in your textbooks, or you can ask your teachers about the advantages and disadvantages. And generally the stepping pulses will be given like this. So this will be your pulses and this is the step number. So your pulses will be like this. So again this will be like this and this will be like this. So this is your one pulse, this is the second pulse, this is the third pulse, and if you are having a higher stepping rate, then this will be like this and this will be like this, so that you can see a higher stepping rate. So this is the pulses and this is the step number. And here one thing I forgot to say is the rotor in the variable reluctance stepper motor is not a permanent magnet. It is not a permanent magnet, but it is a ferromagnetic. It employs a ferromagnetic multi-toothed rotor structure. Ferromagnetic multi-tooth rotor structure. So if I remind you that here the stator of all these three motors will remain same, and the rotor here it is a permanent magnet and it can be of salient pole or it can be of a non-salient pole, and here the rotor is a ferromagnetic multi-tooth one which is not a permanent magnet, and here the rotor is a permanent magnet with a multi-tooth structure. With a multi-tooth structure and it is a permanent magnet. So here I haven't discussed the characteristics and the advantages and the disadvantages of these motors. You can read in your textbook. So already the lecture has gone very lengthy. So I'll stop here. This is all about the stepper motors what I can say to you. So please subscribe to our channel. Thank you.